Today's lecturer is Rolen from Vanderbilt University, and Larry will be about indefinite theta functions and questions. So,
All right. Well, thank you very much, Gabriel, for the invitation. This is my first time in Cambridge, and it's been a lovely visit so far. Very grateful Gabriel just stepped out of the room, but the Gabriel and the organizers for putting together a lovely visit to Red Library, and many of you in the audience were with me with the group yesterday, and get to see some lovely papers of Ramanujan and Hardy, Littlewood, and Newton. The last letter that Ramanujan wrote has played a huge role in my career and birthed a lot of the topics that I'm going to talk about today. It was, I've seen Ramanujan's house in high school a couple times in India on the Shastra Ramanujan Prize trek, and it was a nice full circle thing for me to see the other part of Ramanujan's life, and really cool. All right, so today I want to talk about obviously indefinite theta functions. I want to summarize from my point of view how I think about these things, how some of the, at this workshop, there's been a lot of discussion of modular forms, which are playing an increasing role in physics and swing theory and black holes, etc. And I want to talk about a little bit about the history and, oh yeah, we can watch Netflix on the side. A little bit about the history of indefinite theta functions and how you could think about things like Zwegers thetas and those modular forms, and how you could discover, or in retrospect, how these modular completions work. Okay. And I also want to mention, not just to plug my own stuff, but if you go to my website, right on the front, there's like a link to some notes on indefinite theta functions, and I did a lecture series on the basic theory of indefinite theta functions before, and in particular, I have a number of exercises and stuff there. So at the time, I was like writing several papers with many long calculations on indefinite theta functions. And so, for example, there's certain tricks and there's certain nice examples of indefinite theta functions and other related types of functions. And I have a lot of like very explicit numerical exercises that if you really want to get your hands dirty with some calculations, might be useful. Okay, great. So first I want to talk about modularity in general. How do we find examples of modular forms? And there's basically two main constructions of modular forms in general, right? So in very broad contexts, there's two ways to make modular forms, and almost all other modular or automorphic type things we come up with originally arise from these two examples, together with constructions of new ones from old ones, different differential operators, slash operators with different matrices and combinations thereof. I mentioned differential operators, integrating against things, etc. And those are group averages. Right, so a modular thing is really something which is invariant under a group action, and so you make something invariant under a group action by trying to average over and average some fixed elements, slash it over a whole group, and sum it up and try to fix convergence. So this is like the theory of Poincare series, which I understand Schneider talked about. You talked about Rademacher sums and stuff. So essentially, that was that perspective. And the other way is by things like theta series, namely Poisson summation, which I'll mention in a second. So I'll just say theta. So today's talk is about the second topic. Okay. All right. So let me get into talking about theta functions in general, right? So they're one of two main ways that we can produce modular things with modular symmetries, right? And they have lots of applications, many of which will be familiar to you, right? So representations of sums of squares, or like the number of ways to write an integer with the sum of some number of squares, other problems like that, other combinatorial problems like that. Can you hear the shape of a drum? It's a famous problem. The answer is no, and one solution to this is there's, you find a counterexample, and you can find it with theta functions. My understanding is that theta functions were really studied by Jacobi and other physicists in the mid-19th century because of their relation to the heat equation. And the heat equation and correspondingly the heat operator in theta functions also plays a big role in the modular theory, etc. Okay, so let's give one explicit example. I mentioned Jacobi already. Okay, so this will be the basic theta function theta of tau. It's just going to be the sum of t to the n squared and running over the integers. For me, Q is always e to the 2 pi I tau. And tau is always an upper half plane, which is the set of points with positive imaginary numbers. Okay. All right, so this function, I know the camera can only see up to here, but so this function theta is a weight 1/2 modular form. Now let me write down the transformation explicitly. Right, so this is a Q series in terms of e to the 2 pi I tau, which is translation varying. The theta of tau plus 1 is theta of tau. That's the immediate. The interesting modular transformation is what happens under inversion. And if I write it in this form, theta of -1 over 4 tau is square root of 2 tau over I theta of tau. So I want to sketch very briefly. I think that many of you have probably, if not most of you, have probably seen this, but I want to sketch why this is true. Okay, so there's two basic ideas. Okay, so one, firstly, it suffices to prove. I mean, I already mentioned the first identity is trivial. You really just have to establish the second one. It's sufficient to prove with the imaginary axis, right? Because of the identity theorem from complex analysis. This is a holomorphic function, so I have an identity of holomorphic functions. I just have to show it for tau on the imaginary axis. So that's clear, but we use that in proving lots of modular things. Second idea, as I mentioned, what makes theta series work is Poisson summation. Okay. And let me write this down. So F is the usual Fourier transform. And little f is some real valued function which is sufficiently nice. So we're going to use a Gaussian here, right? But like any kind of Schwartz function or things like that have sufficient decay or whatever that make convergence, absolute convergence work are nice enough. Okay. Okay. So for nice enough functions, if you like, you can just say Schwartz for now. If you take any such function, you add up the value over all integer values of this function. You get the same result if you first take the Fourier transform, then evaluate it all integers and add it up. Okay. So somehow it's like not usually covered in a first analysis course in graduate school or something, but you could. It's not a very difficult thing to prove, really. Okay. And then if you like observation like 2b or something, the next small observation, the theta function, you look at this on the imaginary axis, you essentially have Gaussians. You want to apply Poisson summation, and the Gaussian is its own Fourier transform, essentially its own Fourier transform. Okay. So observation Gaussian is its own Fourier transform, right? And so specifically, I'll show you how you get the 1/2, right? So what you would do here is you take the function f of t is e to the minus I v t squared, where I'm going to say always tau is e plus iv. Then you can take the Fourier transform of f, and you get e to the minus I t squared over v. So this is where you get tau 1 over tau, and then you divide by a square root of v. You just compute this integral transform, and you get this change of variables out, and here's where you see the weight 1/2 factor. All right. I guess I better move this one down. Any questions? So this should just be a basic review, right? But this is the motivational example for everything. There'll be much more complicated examples, but they all work in kind of the same way. I guess I should have started on the back, right? Because only this high is viewable on the kid. Okay. Oh, okay. Well, this is about the extent of how far I can reach, even my height anyway. Okay. Great. So I want to talk about various extensions of this. Okay. So I labeled them maybe 1 through 5 or so. So the first extension is I can make a 2-variable version, as Jacobi already had. Okay. So I'm always going to call e of something for me always means e to the 2 pi I, that thing. And I keep track of a variable z. I call that like the elliptic variable. that's always just a generic complex number, and zeta is its exponential. Okay. So the more general theta function that, again, we already had, is theta of z tau. And there's like a million normalizations of this. One of the really annoying things is that there are many papers, like when I co-wrote a book on harmonic Maass forms, and one of the things we had to do was standardized notation. And one of the really annoying things that we tried to be very, like now, if I standardize notation, I always go back to my own book, because so all my papers from some point on have a standard notation with each other. But there are many papers that there are many different normalizations of this theta function, and there are many papers that just say let theta be the usual theta function, and they don't even say which it is. And sometimes it's even the same function, just different by a multiplicative factor of I or something. Anyway, so this is the normalization that I prefer for reasons of I'm stuck with it. Oh, so it's in the n is in the shifted lattice of half integers, not integers, -1 to the n, q to the n squared over 2, zeta to the n. So they always look like this. You have a sum of theta functions will always look like something like this. We have a sum over a lattice or over a shifted lattice of some quadratic-ish powers, some quadratic q raised to some quadratic form, maybe some prefactors, maybe there's a character or something or some other factor you start with. And then if there's a z variable, you have linear powers of the other. Right? Okay. Right. And this is kind of where I mentioned the heat equation. You can kind of already see it here. There's something about differentiating 1 or 2 times in q or zeta. And anyway, there's linear powers here and there's quadratic powers here. Okay. All right, so what is this object? This is a Jacobi form, which I don't want to formally define, but weight 1/2 and index 1/2. And I can either say it's vector valued, or I can say it's as a multiplier, and then it transforms an SOP. So have a lot of you seen Jacobi forms? I mean, I think they come up in physics a lot. Right, but there's transformations in both. There's a modular transformation in both z and tau, and there's a transformation under shifting tau by lattice points in the lattice generated by integer lattice generated by 1 tau. Okay. All right. So that encodes things like this one variable thing and a lot more information because we have this extra book. Okay. All right. So I mentioned that so we can stick in an extra variable. We can take this quadratic form here, n squared or n squared over 2. And we can make that a quadratic form with more variables. So let's make it a quadratic form in several variables. So what's my setup going to be? Q is from v to the r of z is a positive, definite integer quadratic form. R is some natural number. Okay. And then we'll frequently need the bilinear form associated. We'll say b of x, y, it's a bilinear form, and that's q of x plus y minus q of x minus q of y. All right, so then this is the classical setup. And then we have the following theorem due to Hecke and Schoenberg. I'm also going to mention Eichler-Zaghi just because they wrote it down in this very nice form that I'm getting, but it's really they just attributed Hecke and Schoenberg, but I like the way that they write it down, so I want to mention their names as well. Okay. So what's the result? For any a and z to the r, I can define a theta function, theta sub a theta. We could say it's a theta function with characteristic a's, what we usually say, and we'll define that to be a sum over n in the lattice of z to the r, q to this quadratic form, and zeta to the bilinear form of n with a. Right, so this is still like a linear thing, replacing like zeta to the n here. So you might imagine that a is like a rational number, then you'll get some like roots of unity. So you can pick up things like -1 to the n, or you can take linear combinations, such things, and you can pick up Dirichlet characters and things like that. Okay. All right. So the result is this is also a Jacobi form. Now the weight is r over 2. Previously we had weight 1/2 because it was dimension 1. So it's the dimension of the lattice divided by 2. The Jacobi form has a more complicated index, which is now q of a, and it also lives in some more complicated congruent subject. Okay. And how is it shown? It's like the exact same kind of proof, but you need a generalization of Poisson information in more dimensions. Okay, so yeah. Sorry? I think it's something more complicated than that. Yeah, exactly. I think it's like you can write it as an intersection between two congruent sub. It's not like the level's not as simple as like the discriminant. It's not as simple as that. It can be it's an increasingly complicated congruent subject, but there is some subject. Yeah. I don't have an example off the top of my head, but it's a little less. It's not completely trivial. Yeah. So yeah. Right. So the idea is really it's the same proof essentially works. It's just Poisson summation for general lattices. Right. So you can do Fourier transforms in Rn. You get the same type of result. You always relate a lattice to its dual lattice. It's just by coincidence in this case, Z is the known dual lattice. But there's a general version of that, and I give the general modular considerations here. You know, it obviously takes a little bit of work to really write it down.
Don't introduce shift on the left.
Sorry?
You don't introduce shift on the left.
I will introduce shifts in the lattice. Yeah, for right now, I just wanted to. This is a very classical one without the shifts. Yeah, you could also put in shifts, and then you also get something. And well, this will be a special case of ones later, and then I'll have shifts in the lattice later. Yes, those are important for lots of these. Good question. Yeah.
The lattice is basically by element of the scripting group, or
No, just by like another element in the R. So, yeah, just another lattice element. Yeah. All right, so that's like one thing, and obviously you always have to worry about convergence and absolute convergence, right? Why do we say it's positive definite? Well, what's the size of a typical term, like the absolute value of q to the q of n, right? Of course, like this e to the minus 2 pi v q of n, and anyway, this decays rapidly as n goes to infinity, is absolute value of n goes to infinity, say, right? Because q of n is positive definite, or you can think that as n ranges over z to the r in all possible directions, q of n is positive. As soon as it's not positive definite, there'll be some direction you can head in where q of n, the powers of little q, are becoming increasingly negative, and then you have a divergence problem. Okay. Although we will care about such examples, obviously, because that's the title of today, is we will care about things that are not positive definite, namely indefinite. So that was idea 2, and yes, you can put more decorations and more generalizations, and more of those will be coming, like the shifts of the lattice. But I just want to do one step at a time, where this is just a really classical result, so I like to say it that way. Okay. All right, extension number 3 is we can put more functions in the sum. So like up here, where we have -1 to the n, we can put other stuff there. And let me give one example, and we'll explain where this example comes from later. Namely, when we can insert polynomials, specifically spherical polynomials, spherical polynomials, Gegenbauer polynomials, they show up in a lot of places, even Shimura's famous 1973 Annals paper, right? Like he has these standard weight 1/2 and weight 3/2 stated functions, where you can insert a Dirichlet character and n to the 0, or you might insert an n to the 1 factor in front. That's going to be a special case of this, which we'll see this general theorem about how Poisson summation works, how theta functions work in general, due to Vign&eacute, which is going to explain everything. And we'll come back to that to explain part 3 later. All right, so every quadratic form has an associated symmetric matrix, and there's like always the normalization issue of like whether you divide some terms by 1/2 or not. Anyway, I'm going to formally define it by saying we're going to define A to be the associated matrix, symmetric matrix of the quadratic form, such that q of any vector x is 1/2 times the inner product on Rn of x and ax. Okay. So we also have the Laplacian associated to q, which is like the standard Laplacian but rescaled in terms of this quadratic form. Okay. So delta for Laplacian sub q is defined to be the inner product of ddx, the vector of ddx1 through ddxr, and A inverse ddx. All right. Then finally, I mentioned a spherical polynomial. A spherical polynomial is one which is homogeneous, and it's harmonic, so it's in the kernel of delta, where you have some fixed quadratic form you have. Okay. And then I'll just put, we'll see that then you can define, let's say, theta sub qp of tau for the quadratic form and keeping track of the spherical polynomial. Let's say you take a sum. Again, you can put other stuff in. You can put shifts. I'm just doing one example of a thing you can do. You can take a sum over your lattice, stick in the values of this spherical polynomial, take q to the q of n, and this is now going to be modular of weight. If you didn't have something here, Schoenberg can tell you that the weight should be the dimension of the lattice divided by 2, and the weight of the modular form is shifted up by the degree of the polynomial. So let's right r over 2 plus the degree. All right, and we'll see exactly why you should expect that the degree of p is how much the weight of the modular form shifts. So that's one other generalization. Another is we can restrict the summation and not sum over a whole lattice. Let me just put that under the header restricted sums. You can only sum over part of a lattice, which at first seems kind of like weird. Because then you can't do Poisson. Basically, you can't do Poisson summation if you only sum over part of a lattice. So why would you ever want to do this? Well, it's whenever you sum over the whole lattice, you get a problem. You may want to consider doing that. So motivation, there's maybe two main examples that come to mind for me. If you take the sum over all of a lattice, it's either 0 when you get something totally boring, modular or boring, or it's divergent. So, example, if you take a sum, a one-dimensional one, and you take a sum over z, and you twist it by a Dirichlet character, but you take the wrong sign, so you pick an odd Dirichlet character. Okay, then where chi of n is minus chi of minus n, then you get 0 if you sum over everything trivially. So the natural thing is to throw away the negative integers, which are just a negative copy of the sum over the positive integers, trivially giving you 0. Just sum over positive integers. So you may sum over half and less. Okay. And such a thing, because you only sum over half of it, is called a partial thing. So I have one example here. I'm just trying to keep track of the time. This is an example that plays a role in cat-swapping modal characters and sort of super algebras. There's a lot of interesting things that you can say about partial theta functions, mysterious relations with Mach theta functions as you pass between upper and lower planes. There's a whole story. There's some new things that have been Chenair and Katch and Brinkman have recently figured out how to give modular completions for these things, and there's a lot of cool things you can say about partial theta functions. I might say more if I have time at the end, but I want to make sure we really talk about the classical story of Mach theta functions and Zwegers thesis first. But anyway, let me write down just one concrete example that's pretty cool. So C of Q is the sum of n greater than or equal to 0, the Dirichlet character minus 12 above n, which if your number here seems very familiar to you, q to the n squared minus 1 over 24. And well, this also can be written as the sum of n greater than or equal to 0, minus 1 to the n, q to the n, and plus 1 over 2 non-obvious identity, divided by minus q, Oppenheimer symbol, minus q sub n. Okay, and anyway, let me just say in words because I want to make sure we again keep track of time, but like these things often arise from take appel functions that may arise in. I have an example here that I was thinking about writing about the Andrews Garvin crank function. Sometimes you get partial theta function decompositions of this, or you get certain if you have Jacobi forms of negative index, for example, like 1 over the theta function would be one kind of example. 1 over theta has a really beautiful classical, actually it goes back to the mid-19th century, not in this language, but I found it in some really old book, partial fraction decomposition. And you start looking at coefficients of powers of zeta in the expansion of this. And these are closely tied to, I mentioned Kapswaki modal characters. There's one place these things arise, these Fourier coefficients in zeta arise. And you get functions like this, and they have funny modularity properties. Okay. And there's a lot of cool things you can say about that. Any questions? Did I write something specific about C? Well, again, I think that would take us a little too far astray, but well, maybe I can mention a little bit about this mystery. I mentioned Ramanujan at the beginning and seeing Ramanujan's papers. Ramanujan has this famous quote. You may have also heard of false theta functions. Those are kind of, it turns out you can always go back and forth between false and partial. Partial are like you sum over part of a lattice. False is like some of the signs are wrong. So it's like you sum over a full lattice, the Dirichlet character, but you change some of the minus, the plus and minuses so that it's not actually a Dirichlet character. And Ramanujan has the statement that unlike Rogers in the letter, that unlike Rogers false theta functions, the Mach theta functions enter naturally and beautifully. I would argue that partial theta functions actually do, unlike Ramanujan said, they actually do enter quite naturally into modern modular form theory and modern number theory, but it took longer to maybe figure that out. Anyway, there's a relation between inside. If you think about the disk model with Q, upper half plane is inside the disk, lower half plane is outside the disk, and there's the weird mystery relating Q going to Q inverse, which is like going from the upper half plane to the lower half plane, and then there's these things called quantum modular forms you may have heard about, which have some remnants of modularity, but they live on the boundary of the upper half plane. And if you take Ramanujan's famous third order Mach theta function f of q, and you write it as q hypergeometric series, you let q go to q inverse, you actually pick up exactly this partial theta function, plus what I like to call jump, plus some other q series that the feature is that if you approach any root of unity from below, like along one of these lines, the full asymptotic expansion is identically 0. And at any rational point in the middle, these two things have like a matching asymptotic expansion. Okay. But it's really kind of a weird thing. It's like trying to do mentioned the identity pyramid. It's like trying to continue this function below, from up here below, but there's a dense wall of singularity. So like complex analysis shouldn't allow you to do it. And if you take different representations for f of q, you tend to get the same C function, but like different jump functions showing up. So it's totally not unique, but you can almost make it work. And there's a lot of weird mysteries about it. Okay. Good. So now I want to talk about indefinite theta functions, which is really a subpart of part 4, but I guess I made it part 5 because it's like the main point of today. Okay. So this is like I mentioned part of sort of part of part 4. Partial theta functions arise when you try to sum over just part of a lattice, because if you take the whole sum, you get 0. The indefinite theta functions are where you try to sum over the whole lattice and you get infinity, and so you try to. It's part 5, extension number 5, definite quadratic forms. Okay, so we have the setup will be we have a non-degenerate quadratic form Q, and I'm going to define what type means. There's also kind of a difference of normalization in some papers in literature. I'm going to always call this type R minus S comma S, and this means it has R minus S positive eigenvalues. of the matrix A, if you like. So you can look at the matrix A, say it's non-degenerate, so the determinant is not zero of A, and it has R minus S positive eigenvalues and S negative eigenvalues. Okay. So then if you try to, again, we talked about Hecke-Schoenberg, if it's indefinite, there'll be one direction you can go where the powers of Q are just arbitrarily negative powers of even convergences just out the window. And so you need to do something if you want to make some theta function out of an indefinite thing. So you need to do one of two things or both. Okay. We can either insert some dampening factor. So like when we inserted the spherical polynomial P, that's not going to be a good dampening factor, but you know, maybe you can insert some other thing like the spherical polynomial, which doesn't mess up Poisson summation and which decays faster than the exponential growth of the increasing powers of Q in the right directions. And so fixes convergence. Or, you know, you can restrict the sum just over where you don't have this increasing negative powers of Q. Or maybe some combination of both. Okay. So you need to do something like this for convergence. Okay. And the seminal thesis of Zwegers that, you know, finally explained what are Ramanujan's Mach theta functions after over 80 years. Consider the case of one negative eigenvalue. Okay. So Zwegers' thesis from somehow 2001 or 2002, it seems to, I don't know, it seems to depend on which source you look at or something. Around 2001, he looks at type R minus 1, 1. So for the moment, we'll restrict to this, and we'll talk about other types. So I want to describe what are the functions Zwegers used, what are his modular completions of these of so-called indefinite theta functions, how do they work, and then I want to give the general theorem that explains the context of this and a lot of newer exotic things, and it's quite a broad thing. So namely, this is Vign&Ross theorem that was mentioned in the abstract. Zwegers actually didn't know about Vign&Ross theorem when he first wrote his thesis, but you can see him basically writing down the same kind of thing. You know, I mentioned the Gaussian is its own Fourier transform, and Zwegers even has a sentence in his thesis. He said something like, "Okay, you know, we want to insert some dampening factor. Essentially, we want to figure out when is this. We want to compute that this is essentially its own Fourier transform." And Vign&Ross just figured out a very general condition on when you can guarantee.
So do you need R minus S to be at least 2 or?
No, you can do 1, 1. So I'll have a 1, 1 makes it. Yeah. I need R minus S to be at least 1.
Yeah.
No, I don't require 2. I think I'm going to write down a specific example type 1, 1. Yes. So one of Ramanujan's original 5th order Mach theta functions is a 1, 1. Okay. So let's describe some setup. So there'll be some notation. But I want to guide you through some of how this notation works. So there'll be a certain cone we'll be working with, and you have to fix a C0. Then the cone that I'm describing, that I'm in, is P sub Q, is the set of little c in R to the R, where Q of C is negative. So these are kind of the directions in which you have divergence, where you have to do something. And this is only one negative eigenvalue, so it's kind of a one-dimensional thing here. And well, if you just look at the set of C and R to the R, where the quadratic form is negative, it's kind of a double cone, and you want to pick one of those components. So this has two connected components. That's why you fix a C0. So you can be in the components of C0 by requiring that the bilinear form between C and your fixed thing C0 is less than 0. Okay. If you look at my notes that I mentioned, I give some explicit examples of how some of these things work. Right, but it kind of looks like this, and we pick a C0, so we're just like picking one of the pieces of this. All right, so that's the cone we'll be working with. And very important is also that we work with cusps, where we need to define what are the so-called cusps. And again, not to keep mentioning it, but in the notes I mentioned why you can exactly think of this as I give an analogy with the modular curve, and given a numerical exercise or explicit exercise to sort of work out why you should convince yourself that It's reasonable to call these things cusps anyway. Call it S for cusp, like for Fitson. The set of cusps is going to be the set of C. Let's call the components C1 through CR. Okay, R dimensional vector of integers, which are primitive. So the GCD of all the components is 1. The quadratic form instead of negative is actually 0. And then also you still have B of C from the C0 is negative. And the point is there's a compactification. Okay. CQ bar, the compactification is CQ union S. So you need the cusps in order to get some compacted. All right. So I can now define what Zwegers indefinite theta functions were. Okay. So they're defined in terms of you have to pick a pair of vectors C1 and C2 in this either in CQ or in SQ. Okay. So then you have a theta function associated to your given quadratic form. I've already said it's type R minus 1 summa 1. And it has a characteristic. Now, as we were talking about before, I'm going to allow a shift in the lattice as well. I'll say with characteristic, that's the characteristic A comma B is the above. So theta AB of tau, or there's different declarations like what do I suppress? Sometimes you could write a C1 comma C2. I'm just going to suppress those. Q and C1 and C2 are fixed. You have to make some choice at some point about what you suppress. Okay, so I'll define it as a sum over, well, d to the r, but the A from the characteristic shifts the lattice by A. So you need this to give lots of important examples. Some special function you have to insert rho, depending on n and tau, which I'll define shortly. Okay, q to the q of n is before. And then the exponential of b of n comma b as before. So I like to think maybe b is like some rational numbers, and this is giving me some like roots of unity that are twisting it. And I could take linear combinations and get Dirichlet characters and things like that. And the rho is going to give me some dampening that makes the solve that fixes the modularity and the convergence. Okay. So the game is all about finding a good example of rho, which is what Zwegers had to figure out. I mean, it was a brilliant piece of work, of course. So rho of n tau. What's really nice about this is it actually splits up as a difference of two things. One depending on C1 and one depending on C2. So this is rho, it's a little bit of an abuse of notation, but it's rho C1 of n tau minus rho C2 of n tau. Okay. Now I have to define what is rho C of n for a general B. Okay, and this also has two cases, depending on whether you have a cuspidal point or not. Okay. So generically, it's an error function. There's a lot of notation, so I'll find that in a second, but there's a standard error function of the bilinear form of split C and n times b to the 1/2 divided by the square root of minus q of c. You'll see the square root of minus q of c show up lots of places. That's just a normalizing factor. You could always shift things and not have to do that if you prefer, but then it'll come out somewhere else. So this is again the generic case that you're in CQ. If you're in the cusp, if you pick a cuspidal point, then rho is a sign function, namely the sign of b of c. So finally, I have to define the error function. E of x is, I'm going to say it's twice the integral from 0 to z of e to the minus pi e squared dt. Yeah.
Then we should give this sort of convergence you can achieve in many ways.
Yeah.
But modularity is a much more difficult thing.
Right. So you need to try to identify some function rho that you can stick in that will fix convergence, and such that essentially rho times this Gaussian is an eigenfunction of the Fourier transform, and satisfying both at the same time. Yeah, I could just stick in something I could just stick in like e to the minus x to the fourth or something, and that would make convergence, but like that wouldn't have any nice property under the Fourier transform.
But here you're still in SL2Z, or you're in the double cover to metaplectic group now? Are you still in SL2Z, or you're in the double cover now?
I still SL2Z, or I'll say it in a second, but it'll be vector. I'll consider it vector value in SL2Z. Yeah, and it really is. It's not. It's actually integral way. It's actually not half integral because it's really a sum of. We'll see it in a second, but it's not going to be Maass modular forms. It really lives in the space of mixed Maass modular forms. And so it'll be like Maass modular forms divided, sums of products of theta functions and Maass modular. But just not metaplectic, not metaplectic. Okay. Let me just write it in red. If I want a Jacobi version, just like we had a Jacobi version, we had the original function, theta function, you could stick in a z variable. There's also, this is going to be living in the world of Maass modular forms, you can see. I would just replace this b by general z, where again, z is some variable that lives in the complex form. Okay. That's all you would do if you instead of dealing with characteristic. Just replace the fixed number b by a generic complex variable, then that thing is going to have a Jacobi transformation in both z and tau.
Is this solution unique?
Is what solution?
Is solution unique?
What do you mean by solution?
You can insert, as in the previous case, you can insert all the polynomial.
Yeah. There's no claim about this row, for example, being the unique thing that you could do that with.
So what is the property that fixes this solution?
What is the property that fixes this solution?
Have some indefinite quadratic form, and you want to have a sum over the lattice or shifted lattice q to the cube n times something that makes it modular, and like this is a good one. That's one way to do it. But it's not so easy to find study. Yeah. It's already a major accomplishment just to get one. I mean, so we'll talk about how do you generate all of them. Or how do you naturally, well, I have no claims about when I mention Vign&eacute, I'll give a condition that will guarantee that certain things are modular. I guess that doesn't necessarily prove that they're everything that's modular, but it's kind of built in a way that, I mean, we don't have a lot of ways of generating modular forms. Like we have Poisson summation, and Vign&eacute like did the calculation to like figure out exactly which things will work naturally with Poisson summation. But that's not to say there can't exist other things that are modular for other reasons, or maybe it's not an eigenfunction of the Fourier transform, but for some really weird reason it still happens to work out with Poisson summation. But it's hard to believe that there's much else other than I can ask the question.
You can ask the question of stability, no? So you can ask, is there a smooth deformation away of this choice of row that you gave, such that you preserve modularity?
Yeah, well, you can definitely do a smooth, and we do need that at one point. You can definitely do a smooth deformation of the C1 and C2. You can parameterize the space where they live in, and you can put in an extra variable t and smoothly deform these, so then you do get a family of those. So you can do that.
Is it possible that, for example, I take Q here, construct its Weyl representation, and I now know how, under the metaplectic group, how the theta function transforms, and whatever extra piece I get out under this transformation, can I repackage that into rho somehow? Would that be a way to determine what rho is?
Maybe. Well, maybe it'll be more clear once maybe we can revisit that when I give Vign&eacute.
Okay.
I mean, if you want to make Poisson summation work in a natural way, the only way we really know how is to make something be an eigenfunction, make this whole thing be an eigenfunction of the Fourier transform. And that's essentially equivalent to a differential equation we could write for rho. And I'll talk a little bit about, I know one way to find some solutions. I don't know how to characterize all of the solutions. But yeah. Remember Zwegers' original goal was there were these theta functions, and Andrews and Hickerson and Watson and others had generated new examples of theta functions, weird relations between them. Dyson was starting to ask, like, they should play a role in physics. There should be some vector space structure that they live in. He said additive structure or something like that. And there was a menagerie of examples and near miss modular transformations and linear relations among them that begged an explanation. So the goal was to find some explicit family of functions that included all the ones that people wanted to understand. Okay. Right. So let me now write the theorem of Zwegers, which we want to explain. Okay. So under some minor assumptions in C1 and C2, which are just for conversions, this gives a vector valued Jacobi form of weight R/2 on SO2. And if you pick one with characteristic, then it'll be a piece. If you pick the one with characteristic without the z variable in it, these are pieces of vector valued so-called mixed Mach modular forms. And what is a mixed Mach modular form? These are sums of products of modular and Mach. Sometimes you actually get ordinary, so we'll see this in a little bit, but sometimes you get lucky and you don't get a mixed Mach modular form in some of the examples, like the ones in Ramanujan's letter, actually. And you can get away with actually discovering a Mach data function. What you end up getting is you get a decomposition. You get a finite sum of Mach modular forms times modular forms. And sometimes each of those components, just by coincidence or by some extra internal symmetry, is the same modular form, so you can just divide the whole thing through by it and get an ordinary modular form and not a mixed modular form. But somehow the space of, and this is Zaghi's philosophy, for example. Zaghi always likes to try to emphasize, and so do others such as Pablo Perjoy, et cetera, that mixed Mach modular forms in a lot of ways are a more natural space to work in than Mach modular forms. They should have more attention. All right, so Zwegers had what I like to call a threefold way. In his thesis, he had 3 different ways of attaining the same functions: Appel-Lurch series, coefficients of meromorphic Jacobi forms, and data functions like this. I think we should probably get on to Vign&eacute theorem rather than talking a little bit about this. Okay, so I want to see, the big question is, why is this true and how does Zwegers theorem work? Okay, but first I want to talk about the relation to Mach modular forms explicitly. Okay. So there's a key identity. I'll call it equation star. It's just a simple special functions identity. It's a little exercise if you like. This error function has a representation as sine of x times 1 minus beta of x. And I have to define beta, right? So beta is a standard expected function, beta of, okay, I'll just say y. Y is a generic variable, so that's integral from y to infinity, t to the minus 1/2, e to the minus pi, t, d. And if you're a Mach person, this is valid for y, positive real number. And if you're a Mach person, you like incomplete gamma functions, you've probably seen throughout the Fourier expansion. This is 1 over square root of pi, incomplete gamma of 1/2 pi. So I want to see how you can get the Mach in the Mach part of these theta functions that he writes down that are non-holomorphic modular forms, and how you can also obtain the shadow of these things, which Zwegers shows you how to do in the thesis, but he never explicitly actually writes down. I mean, this was a little bit before Bruni and Tuke defined what a harmonic Maass form is, defined the shadow operators. It's essentially the lowering operator, which is more or less the way that Zwegers wrote it down. He gives you all the pieces you need, but it was before we were talking about Mach modular forms in the modern sense in shadow, so he didn't write down the shadows. Anyway, so there's another key fact about this function rho. Okay. So there's a special decomposition. So right. So I'm going to give more notation. If J is 1 or 2, I'm going to define rho sub J of n tau to be, okay, so this is a new definition, minus 1 to the j, the sine of b of cj comma n. As you can kind of see, and then it's a beta function, I'll write it down, but let me say in words, like, as you can see, a lot of the business of making stuff work you do at some point have to prove certain special function identities. Okay, so something plugged into this beta function. Okay. And I'm going to define another function, rho sub 3. Kind of seems strange, but bear with me. Okay, that's going to be defined to be a difference of sign. These differences of sign functions are the type of functions that actually occurred in the way that Ramanujan and Andrews and Watson and others actually wrote down examples of positive functions. Just the difference of sign functions with the bilinear form of n against C1 and C2. Okay, so here's the decomposition. Right, like I'm not going to prove this, but this is, you know, you could do it with explicit computation. Rho of n tau, the thing you insert to define the Mach modular form, define the completed Mach modular form, is rho 1 plus rho 2 plus rho 3. If both C1 and C2 are in CQ. It's rho 1 plus rho 3 if C1 is in CQ, but C2 is in SQ. It's rho 2 plus rho 3 in the opposite case, where C1 is a cuspidal point and C2 is not. And if both of them are cuspidal, S for cusp, not C, then it's just equal to rho 3, a different sign. So let me write kind of thinking of holomorphic and non-holomorphic parts of modular of harmonic Maass forms. I like to define theta plus with all the decorations A, B, C1, C2. Let's not write all the decorations every time. So this will be a sum over n in A plus e to the r, rho 3 of n tau, E of B of exponential of bilinear form of n against B, q to the q of n. Okay, so it's really just the sum of q to the quadratic form, some like twists, maybe some roots of unity and stuff, and then differences of sign functions. These are the forms that Mach theta functions were written down by Andrews, etc. Ramanujan's original functions were written like this, and it's written suggestively like this is supposed to be the Mach modular part, the holomorphic part of this overall completed. Okay. And theta minus should be the rest. Okay, so it should just be the same, the sum over the same of, well, everything should sum up to rho, so it should be sum of rho minus rho 3, and then all the same stuff. Okay, so that theta equals theta plus theta. Great. Any questions on this? I want to describe what the shadow of this is. I think it's just a nice thing to do hands-on. It is a menagerie again of special functions, but it's nice to do. Nice to get your hands dirty sometimes. And again, it's something that's like written in Zwegers' thesis. It's implicit in Zwegers' thesis, but he doesn't write it explicitly. So it's nice to see how these things work. And I mentioned mixed Mach modular forms and how you really have to consider not Mach modular forms, but sums of finite sums of Mach modular forms and Mach modular forms. And this shows in a very hands-on way why that happens. Okay, so there's a very special function that occurs in Zwegers' thesis, RAB of tau. Okay, this is the sum of n and a plus b. So, well, a and b are fixed here. Sine of n, beta of 2n squared b, e to the exponential of minus nb, e to the minus n squared over 2. Okay. And while there's sort of weird non-standard unary theta functions that occur in Zwegers' thesis, or like I say weird because they're not the ones that you wrote down, but they're the ones that are convenient for this framework. Okay. But there was me and Deacon Americans and Ken Ono did eventually write a paper where our goal was actually to use the standard ones with Dirichlet characters like Shimura uses that are more standard, and find the Mach modular pre-images of those. And anyway, this is the original example of Zwegers.
Quick question.
Yeah.
So this theta here is for fixed characteristic A and B.
Yeah, for fixed A and B. Okay. So I was just suppressing it just to.
But on the modular transformations, they can transform into each other.
Yes, exactly. So Zwegers uses these unary theta functions, just one variable theta function, sum over n and a plus d, n exponential of nd q to the n squared over 2. Okay, so if you've ever worked with Mach modular forms, you know, the key point is that there's a shadow operator, which maps harmonic Mach forms surjectively onto the dual weights 2 minus k space of plus forms. Okay, it's called C sub k. Okay, and there's a little factor, multiplicative factor, we get 2i, and you take the imaginary parts for k, bb tau bar. All right, I've had lots of people complain about this notation, right? This means if you apply to function f, you should stick in the f here and take the anti-holomorphic derivative and then conjugate. I once had a referee report which compared it to this famous. Has anybody ever heard of this? There was this famous talk that like Maass gave where he was trying to annoy somebody in the audience. So he defined something to be capital C. So there would be the expression capital C conjugate divided by C. So one referee compared it to this and said, you're not allowed to use this notation. But I said, well, we said, well, it's kind of standard. We can't change it now. So sometimes I write it like this because that makes more clear. Okay. All right. So that's our shadow operator. Basically, the point is that if I apply the shadow operator to the R's, I get the G's. Okay. So shadow operator sub R over 2 of RAB. Again, this is all in the thesis. This is minus B to the R minus 1 over 2. Okay, there's times square root of 2, whatever. Times GAB, what else? And the shadow, the shadow slash the non-holomorphic parts are determined by special decomposition. This is really kind of one of these things where you say math isn't a spectator sport and you really understand it when you do it yourself in some explicit examples or something. But let me write, you know, how I'm going to make some claims about how you can write some decompositions, and it's not that hard to show, but you know, we won't have time to do it in full detail. Okay. But at least hopefully it gives like a general. I always want you to walk away with like a general picture of philosophy of like roughly how things work. The little details I always say, like for any paper, this is like Zwegers thesis and well-established into the literature. You know, you can always find more full details on the archive if you want. The idea is to get the general idea that if you do want to read it, you go in with some general philosophy. Okay. Okay, so here's what I want to say. If Cj, that's C1 or 2. Okay, that's in our compactified state CQ. And let's say it has integer coefficients. And it's primitive, so it has relatively prime coefficients. We're going to take a sum over n. Okay, and I can write any such n in my summation for my indefinite theta function as L plus capital N Cj, where L is in the shifted lattice A plus B to the R, capital N is an integer, and I choose L so that the bilinear form of Cj comma L divided by this normalizing factor 2 Q of Cj is in intervals with 1. So in 0 to 1, not including 1. So when I write, when I write these kind of sums over n, I can decompose them as sort of just shift. I can renormalize it. I can just write them in decompositions like this. And then I want to decompose further. So this is an elementary claim that you can check. The set of L and A plus Z to the R. So it's just some basic linear algebra such that the bilinear form of CJL divided by this thing 2Q of CJ is in 0, 1. This has is a disjoint union of some smaller dimensions of this. So this is a disjoint union of L0 in some special set P0, J. L naught plus the orthogonal complement in Z. So this is the set of things in Z to the R which are orthogonal to Cj, shifted by Lz. Okay. When the point is this is a computable, P0J is a computable set and it's a finite set. So this is a finite thing. And what else do I want to say? Okay. These are dimension 1 smaller. These are smaller dimension, and because spheres only work with one negative eigenvalue, basically you're splitting away the negative eigenvalue. You get a decomposition as a disjoint union of a bunch of shifted lattices. These are dimension 1 smaller, and these are now positive. The quadratic form is now positive definite here. So theta functions for these things, you know, are just automatic. They're already defined. I don't have to insert any defining factors and stuff. Okay. All right. So then I want to write the equation. This is where, again, I say you can look at archive, or we wrote this equation explicitly in my book. I'm just going to write the flavor of the equation to just make it fun. So I have my like general theta function of Zwegers. I apply the shadow operator. This is supposed to be weight R over 2, so I should apply the shadow operator weight R over 2. Okay, equals dots, so up to a constant. Okay, the constant square root of 2, but it doesn't show anything in the formula. Well, okay, square root of 2b to the R minus 1. So some little factor. And then what you'll get is you'll get a sum over the finite set P0J. So this is like the shadow of this thing, right? Of some. If I take a form and I write superscript C, that means conjugate, take a complex conjugate of the Fourier coefficients. Which, if you've seen, you know, you can also like take minus tau bar bar. You can do that as an operation, but I just take the complex conjugate of the Fourier coefficients. Some appropriate A and B values. You have a sum over this finite set, this decomposition control, how this sum works, a complex of conjugate the Fourier coefficients of a bunch of unary theta functions. And then you multiply by sums over this L0 plus the perp space of Cj of blah 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 Q to the QR. And the point is that this is these things, and then you take a complex conjugate here. And the point is that these things are R minus 1 dimensional positive definite theta functions. I know this is like kind of vague, but this explicit, I think this decomposition I think is relatively explicit. And you take, you know, you have to insert the right parameters. Again, writing them out almost doesn't give more intuition. You get, but anyway, this is like roughly how the decomposition works. Okay. And this is why you do need to consider sums of modular form. You need mixed modular forms, because the shadow is not really a modular form. It's a finite sum of modular forms times conjugates of modular forms in a different way.
What is P0 again?
P0 is there. I'm claiming there exists a finite set P0 such that the set of all L in A plus E to the R with this condition, with this bilinear form, and then 0, 1, naturally splits into a finite collection of shifts of this single perp space. And the representatives of those shifts are the set P0J. So I'm claiming that there exists such a set, and you can effectively compute it in any case.
So is this finite set of rational numbers, or?
Yeah, it's a finite set of rational numbers. Exactly. Take one of
This
in one sense. Yes.
Only for the case that C1 and C2 are.
Mm-hmm. Oh no, this is a CQ bar, so this includes that at all. It works the same.
I see. Ah, okay, thanks.
Okay. All right, so I just want to give the flavor of that, because again, it's how you actually can do things in practice. And I know I didn't write all the decorations, because after a while, you know, we're just again, this is not a spectator sport. You have to sort of work out explicit examples yourself to really get it. After a while, it can feel like a menagerie of special functions, and I just want to give the general idea. So just to make everything totally explicit, I want to write down two very explicit examples. And then I want to talk about Vign&eacute.
Sorry, I have a question from the audience. What notes are you talking about?
About notes?
Yeah.
Oh, if you go to my website, it's like on the very front, there's a link that says notes on indefinite data functions, and I wrote like there's like 4 type notes with some more details.
Okay.
All right, so example of when we were talking at the library about order of mock data functions. Ramanujan used a term called order, which he didn't really define anyway. Sometimes we still use this phrase, these phrases about the order of them. So he had a 5th order mock data function and called f0 of q. Okay, so he wrote this in a q hypergeometric way, or we saw it in the letter. He called it Eulerian series, which is a Ramanujan specific term, maybe, or by that he just means q hypergeometric. But let me define it this way: Andrews proved an identity for this function of Ramanujan, and Andrews had proved a number of identities like this. Okay. So Ramanujan's function is 1 over the q Cochran symbol q infinity of a difference of 2 double sums of an indefinite quadratic sum. Okay, so in the literature, these are often called Heck type double sums. So this is a sum over n plus j greater than or equal to 0 and minus j greater than or equal to 0 minus the sum n plus j less than 0 and minus j less than 0 of, we'll just keep going this way, minus 1 to the j, u to the 5n squared over 2 plus n over 2 minus j squared. Okay, and a very instructive calculation to see how all this works is figure out I'm going to write down the cleaned parameters, but you can actually just explicitly write down the definitions I gave and find that this is what I said. So this comes from the type 1,1 indefinite theta function. Okay, that you can find in Zwegers thesis. So okay, q to the 1/60th. You always need some. Ramanujan's mock data functions aren't quite mock modular forms. They are up to a rational power of q. My understanding is in physics, you have things like central charge, and these rational numbers mean something very specific in physics interpretations. But for us number theorists, you need some. There's the fixed rational power of q. You need to fix modularity, and anyway, here it is. The eta function, which is just, if you haven't seen it, it's just q infinity times q to the 1/24. All right, and then so I take times the sum n in a plus t squared. So how do I write this thing naturally? I write this as a difference of sign function. Okay, which we've already seen come up. So the difference of sign function is the bilinear form of n against c1 and n against c2. Ooh, I gotta write b. Maybe I'll write square brackets here. Okay. Right, so if I have a difference of sign functions, you just have to look at the cases. Okay, there's the boundary cases where, depending on how you define it, you can get a 0 or whatever. But these are like plus or minus 1s, right? So you could get a 1 minus a 1, or a 1 plus a 1, or a minus 1 plus a 1, etc. Right? And sometimes these will cancel out and they'll contribute nothing to the sign, and sometimes they'll double up, but with a minus sign, right? So you just have to keep track. I'm going to write down the parameters, but you can directly write down for these parameters. I'm going to write out like these are the terms that survive, and like sometimes you get a doubling up and you get one term survive, and sometimes you get a doubling up with a minus. Okay. All right, and then q to the q of n exponential of bilinear form of n against b. Okay, and here's your q. This should be your quadratic form, and your exponential of the bilinear form of n with some fixed b should give you these roots of unity minus 1 to the b. Okay. So let me write down all the parameters. Just to be very explicit, at least one. So qjk is the quadratic form 1/2 times 5j squared minus 2k squared. Okay. So I lied. Here's the 5n squared over 2 minus j squared. You can see that. But there's an extra linear term here. So this n over 2 should also go inside of it. All the linear stuff and all the roots of unity have to come from all this. Anyway, or have to come from, you can also, they also have to either, or shifting the lattice, right? You shift the lattice and then you get a linear term. But you can also include a Jacobi form and also get linear powers of Q down. Anyway, let me just write the parameters. So A is 1/10 to 0. B is 0, 1/4. T1 is 2/5. And T2 is minus 2/5. And it turns out that C1, C2, those are both those are in CQ. And F0 of Q is Q to the 1/60th divided by 2 eta of tau times the theta plus I wrote before that I wrote down a little bit about, at least philosophically, like how do you find Chet, or what are the key identities to find the Chet. All right. So that's like one example, and you can kind of see if I have some explicit example, you can see what the quadratic form should be by looking at the expression. I can figure out what the shift should be. I can figure out what the B should be pretty quickly. You know, I need to maybe make some, I could just make some variables for the components of C1 and C2 such that a difference of sign functions is going to survive exactly in these conditions, and you can solve for them and you can find your C1 and C2 quite explicitly in any example. All right, and I want to just give one kind of general thing. So with remaining time, I want to talk about some of the higher depth things as well and how they work. These are modular forms. There's this graded vector space structure on the so-called higher depth things that you may have heard a little bit about, where ordinary modular forms are depth 0 and Maass things are depth 1, and then there are higher depth 1 things. And like generically, the depth of the indefinite theta, the completed indefinite theta function thing should be the number of negative eigenvalues, but sometimes it's actually lower than you expect because there's an extra internal symmetry. So like sometimes, you know, you have a depth 2 thing and it's really a product of 2 depth 1 things for a trivial reason, or sometimes you write down something in Zwegers thesis, it should be a Maass thing, but actually because there's some extra symmetry, you could think that non-homomorphic parts cancel, or however you want to think about it, and it actually is a classical modular form, not a Maass one. So there's one really cool example that I like. Anyway, it's eta squared of tau. That's a really cool. So I think Hecker wrote this one down, and maybe this is the reason we call these things Hecker-type double sums. And he wrote down this really cool identity as an indefinite theta sum. So it's the sum of n, n greater than or equal to 0 minus the sum of n, m less than 0 of minus 1 to the n plus m q to the n squared over 2 plus 2m n plus m squared over 2 plus n over 2 plus m over 2, okay, plus 1. So you could also do that by Zwegers thesis, and then, you know, it wouldn't a priori be something Mach, and it happens to actually be Mach. Okay. All right. So you can think that if your quadratic form, if it has like, if there's extra symmetries in the modular form, the philosophy is sometimes it tends to simplify the modular forms or lower the depth somehow. All right, so any questions? I want to get to Vign&eacute theorem. So I wanted to talk about Zwegers thesis. How do you use an example? What's an explicit example? How do you figure out the shadow of things? What are the tools that are in pieces that if you need to use them and you want to compute in a specific case, how do you do it? But there was the big question of why are these things actually modular, and so I want to address that. Okay. So I mentioned like 10 times now Vign&eacute theorem, which is how I would now think about how Zwegers thesis works. Zwegers, like by brute force, was solving the same problem but less general. Yeah.
Well, so you're repeating words the shadow operation on the theta function. So what did it give you?
Oh, like
thing
if
you
you
just-
take one of Zwegers complete, if you take one of Zwegers theta functions. Yeah, so you take this decomposition that I mentioned, and you get a sum of unary theta functions, but with their Fourier coefficients conjugated, times complex conjugates of all of these r-1 dimensional positive definite theta functions. So you get something that's in the, we would say that the shadow, it's in weight r/2 of this thing is in, so you get those unary theta functions are all weight 1/2. And then we would write tensor m r/2 minus that conjugate. meaning it's a linear combination of 1/2 things times weight r over 2 minus a half base conjugate.
Okay.
Yeah, and explicitly in both cases they're all theta functions, and they're all shifted theta functions of the same lattice here. But remember, we started with the type r minus 1 form, so we have one negative eigenvalue, and then by doing this decomposition, you have a finite collection of theta functions, but they're all one-dimensional smaller, and you get rid of this problem with this negative eigenvalue. They're all positive. Yeah. Okay. So, well, probably not pronouncing Vign&e's name totally correct. There's an accent on the E, so maybe it's Vign&e. I'm not the best at French, and my pronunciation of it is probably fixed by now. But Vign&e wrote down this amazing theorem in the 70s. And it basically encapsulates when functions are in this context, or right in a second, are their own Fourier transform. And by functions, I don't mean like the space, all functions in some Hilbert space. I mean specific functions that were like. All right, so let me just write the thing. And this theorem will encapsulate all of the results we've seen before, so far today, and also more modern things, like pretty much everything we know about all of these kinds of theta functions and newer types of exotic non-holomorphic theta functions, and they all follow from Vign&e. So I'll just write V for Vign&e. Okay, so Q is an integer quadratic form of type R minus S. So in particular, it's a non-degenerate quadratic form, but it could be positive definite, it could be negative definite, or indefinite, I don't care. So P is going to play the role of rho. So I want P to be a function which is going to play well with Poisson summation and make modularity work. So I want P to be a function from R to the R to C, and I want it to satisfy a special differential equation for some number lambda, which is an integer. Okay, and here's the differential equation that makes everything work. So there's something called the Euler operator. I'll define in a second. We've already defined the Laplacian to be scaled by the quadratic form delta Q, and well, I divide by 2 pi. So this difference of these two operators, we want P, that function, to be an eigenfunction with integer eigenvalue of that alpha. So E is Euler operator. Okay, and this is the sum from j equals 1 to R, xj d dx. And then what is her theorem? Under convergence conditions. And here I explicitly didn't want to write them because I think she expresses it as you're in the intersection of an L2 and an L1 space. Anyway, Zwegers' example fits into this framework, and it directly violates Vign&e's. So Vign&e's theorem is even more flexible than Vign&e's states. So like, as long as you can justify the convergence at the end, as long as the equation star as long as the equation star works, and you can somehow make convergence work, it's fine. So Zwegers' thesis, like Zwegers' brilliant idea, in some sense, was again that this Vign&e's theorem was known, was used by people for a while. Examples like Zwegers' indefinite theta functions weren't found because, again, they failed the convergence. But Zwegers' idea is you have to take a difference of two things of the shape of Vign&e, and then you fix convergence. So that's why everything is always a difference of there's a C1 and there's a C2, and you take a difference of two things. Because if you didn't do that, you would have no convergence, and yeah. Right. So don't worry too much about the convergence. Huh? Oh, so delta Q is the ddx is the vector ddx1 and ddxr in inverse ddx. Okay, great. So then here's our theta function. So okay, you have some like power b. This is pretty standard stuff. Right. So b to the minus lambda over 2, whatever. We have a sum over this shifted lattice. This p function you insert, but you don't just insert n, you insert square root of b times n plus y over b. And then you do the same stuff we've been doing, exponential of bilinear form of n with c q to the quadratic form of n. Okay. So this is and maybe he didn't use this language, but anyway, her result could be interpreted in this way. It's a vector valued Jacobi form of weights r over 2. So that's, if there wasn't a p inserted, this is a classical positive definite data function, the weight would be the dimension of the lattice divided by 2. And if it's shifted by this eigenvalue. All right, so that's the big theorem. And again, this is basically what she did. As she wrote down conditions on, she is bold enough to ask, what functions p, one variable function or r variable functions can I insert that will make this thing modular by Poisson summation? Well, I want this overall thing here to be essentially I want that to be like an eigenfunction of the Fourier transform. And she just massages it and this is the key equation that makes sense. And then she wrote down convergence conditions that guarantee absolute convergence, but again, that's not even necessary anyway, because as long as you can a posteriori or whatever justify absolute convergence, it'll all be fine. Okay. Yeah, so I want to write down, that's what I want to do. Yeah. Good question. Yeah, for example, let's do the spherical polynomials. Okay. So P is a polynomial of degree D. So I want to say it's a homogeneous as well. Okay. So it's a general fact from analysis, I don't know, I've seen it as an exercise in an analysis book, for example. A general function is an eigenfunction of the Euler operator if and only if it's a homogeneous. The same is true for polynomials. A polynomial in particular is homogeneous of degree D if and only if it's a degree D eigenfunction of the Euler operator. So that's kind of what the Euler operator does, is it determines homogeneous functions. Okay. And if it's a spherical polynomial, we require that it's in the kernel of delta Q. So if you do E minus delta over 2 pi on P, you get dt. And so this recovers our weight r over 2 plus the degree of the spherical polynomial theta functions from B. It also recovers, so it recovers Peck-Schoenberg. If you insert the spherical polynomial, it also recovers that. Right. So I want to see how it also recovers Zwegers' thesis. Okay. So maybe this is example 1, example 2. Okay, how to solve in general Wiener-Roth equation. I have a little space and say star, how to solve star in general. And well, the answer is I don't know in general. I mean, I don't really know how to solve very generic dimension D or dimension R differential equations like that. But there's a trick. So Zwegers' thesis, and not just Zwegers' thesis, other examples of these types of theta functions you tend to see all really, I haven't seen this written anywhere explicitly, but I mean, it's clearly known to experts or whatever. But I don't know, I get a little intimidated by degree R ODE. I don't know how to solve them in general, but there's a way to turn this into a one-dimensional problem, and then it's a one-dimensional ODE, which is completely solved, and that gives Zwegers' thesis and others. Okay, so here's the idea. It's quite a natural thing anyway. Make this a 1D problem. Okay, so let's fix some C with Q of C, some vector C with Q of that thing is negative. Okay, so let's pick a one variable function. And from that one variable function, I can define a R variable function B to be the one variable thing where inside I stick a bilinear form of x against my fixed vector c. And then just for rescaling purposes, again, the square root of minus qc whatever, like Zwegers also talked about this. You can rescale everything so that's not there. It's just a nice scaling factor. It doesn't really. Right. But basically, if I have this one variable thing f, and I want to find an r variable thing, I can just like take bilinear forms of my r dimensional vector against some fixed. Okay. So that's a natural way of just like rescaling, boosting this one variable thing to an r variable thing. And then this, I know I've hidden it with this board. It satisfies Vign&eacute equation star. It's a very easy calculation to check that this just directly converts it to a very simple ODE. So the Euler operator, right? That's the sum of xi d dxi. That just becomes, well, I wrote z. I guess I'm going to call it. Well, I'll stick with okay. So that's just the one. If this is a function f of z. So the derivative with respect to z times z. This is the translation of the Euler operator. And then the Laplacian gets rescaled, so then I'm also kind of rescaling by the bilinear form, and it kind of undoes it. So this just becomes an ordinary second derivative. Right, so this corresponds to delta q over 2 pi. That should be like that. So now this is like a one-dimensional. This is satisfied when g is specifically of the shape, if and only if this simple equation is satisfied. And like this one is pretty explicit, is solvable. And in fact, it's related to a very famous one. Okay, which is y double prime plus 2x y equals 2ny. Okay, so you can kind of translate it to this form, which like there's like I think even a Math World or Wikipedia entry for this function, for this difference function. And maybe I can conclude. I think we started 1 or 2 minutes late, so let me just write a little diagram. So we boiled everything down to, okay, this is one very natural way to solve the problem. Again, it's not all of the solutions of Vign&eacute equation, but it's like one really nice way, natural way to find solutions to Vign&eacute equation. And it all relies on solving this equation double star, which I'll put here. Okay. And double star has two families of solutions for integer eigenvalues n, for integer values n, and there's a splitting depending on whether n is positive or negative. Okay. So all of the solutions of this are known classically. They are iterated integrals of well, complementary, but essentially just error functions or 1 minus error functions. Okay, so like n equals -1 goes to Zwegers, give you the Zwegers thesis example plugging it into Vign&eacute. If you go more negative n, they're just iterated integrals of the same thing, and there are certain relations. I mean, you get more of the same sort of thing, essentially. Okay, for positive n, so this is like the n negative, and there you have more convergence issues. And again, Zwegers thesis, it does not satisfy Vign&eacute, but you take a difference of things instead of a single function, it fixes convergence, which is kind of amazing. Okay, n is greater than 0. There are also solutions, and you get other nice examples of things. And the solutions of this equation are like Hermite polynomials. So say h sub m of v or h sub n of v, let me say. Okay, so it's the exponential e to the, let's say, it's all normalization, but this Gaussian e to the 2 pi z squared times the nth derivative of e to the -2 pi z squared. So right, you differentiate, keep this factor, the exponent keeps surviving, and then you kill it at the end, so you're left with a polynomial. And Stoffel did some work on this, on what modular forms you get out of this. Okay. All right, and maybe with 1 minute left. So I also like to ask the general, I can ask the general question of like, this is one way to solve this equation. You get Zwegers thesis and other things that are also in the literature that are beyond, that are not in Zwegers thesis. If you can find other interesting solutions, particularly you can get other interesting functions. And let me mention one other thing that goes beyond this, and that's the sort of higher depth. If I had more time, I could talk more about that, but let me just mention. Okay. It was a big mystery for like 20 years. What about theta? What about how does Zwegers' thesis work for indefinite theta functions of type r minus s, comma s, where s is bigger than 1? Okay. So there was a big and Zwegers and Zaghi were working really hard on this. I think they had some partial solutions. They were working anyway. There was a huge breakthrough. Well, maybe more like 5 years ago. Okay, I like to think it's a few years ago, but maybe I'm getting older or something. But Alexander Banerjee and Healy had a big breakthrough where they solved the case s equals 2. The point was you had to use Vign&eacute. You have to find a special function p which satisfies this equation, and it was really a struggle to find a nice example of a function that did the job. And it was really inspiration from physics, is my understanding, that allowed them to really find it. So there were certain natural integrals. They're called double error functions. Is what they end up using. And I guess that they're kind of Penrose type integrals, and they were very natural from a physicist point of view. So the number theorists were many number theorists were trying for a long time to solve the problem. They couldn't find the function p that satisfies Vign&eacute, and it was physicists with physics intuition allowed them to find the right examples of special functions. But then we also have Chenair in the audience. He figured out, he generalized their work to s bigger than equal to 3. And yeah, and then, so anyway, you can do any indefinite theta functions of any signature now. And then, you know, if I had more time, there's more exotic things. There's even these things that Zwegers called Maass theta functions, which, anyway, it's a total parallel world. It includes, it's a parallel world to Mach modular forms, which as Mach modular forms start with holomorphic modular forms and then give you non-holomorphic things. In the parallel world, there's a parallel notion of shadow operator, and you start with Maass waveforms, and then you get things that are almost but not quite eigenfunctions under the Laplacian of weight 0 eigenvalue of quarter. There's just brand new work in the last few months on that, and I like to I'm happy to talk with anybody about that, but I like to promote that work of Zwegers on this alternative theory because there hasn't been much work done in that theory since, and I think that has a big role to play in the future. There's a lot of important things you can probably say about them. I imagine that they're very important functions. For example, in physics, I would almost bet that there's some important interpretation of these functions in physics. And it's just to say, I just wanted to also mention to say that there's a whole menagerie of there's many different more modern types of theta functions and things that live in this world, and they all kind of can be encapsulated in this one theorem of Vign&eacute that everything flows through. But again, so finding explicit solutions to this that do the job you want to do in some particular problem is not necessarily easy. And it's a very explicit equation, but it's not always easy. And I put under convergence, and I say don't worry about it too much. But like, you know, as you may know, right, in a lot of these types of problems, establishing the convergence might be the hardest part. It might take a serious amount of work. Okay, so I think I'm 2 minutes past time, so I'll stop here.
Yeah, so you mentioned, apologies for the broadness of this question. Okay, in the very beginning of your talk, you mentioned that there were two sorts of constructions for modular forms, one a Poisson summation and theta functions, and one did a group averaging.
Yeah.
And I was wondering if there is like a nice sort of story connecting these two constructions.
Well, I don't think so. I think they're
totally
different approaches. Yeah.
Okay.
Or I don't know, Jennifer, do you have any? I think they're just totally alternative. I mean, do you know what I mean by when I say group average? Like,
every say modular form is invariant under some group action, so you have a group. So maybe it's like a trace over.
yeah. So like, yeah, the group acts on functions on the upper half plane. Okay, by say Peterson slash action. Anyway, a modular form is something which the function slash with gamma is invariant under that slash for all gamma in some group, right? And then so you just take some t function, just take some function g, slash with gamma, and then let gamma range over the group. And well, assuming convergence, which is a big issue, and you might have to modify this, you might have to quotient up by a stabilizer, and you have to really work carefully to get absolute convergence. But like if this were a finite group, it's just like a general algebraic thing, right? If you have a finite group and you want some element of group, and you have a group action, and you want some elements the set acted upon that's fixed, just like pick some element of the group and add up the slashes over the whole group, and that would be. Yeah. But I don't know a direct relation. It's just these are the two prongs of like these are the ways we usually produce automorphic forms in general. Yeah.
Can one apply Vign&e theorem to the weird cases like quantum modular forms? Or
Yeah, well, quantum modular forms. I mean, okay, I like to say something like all of these. There, Mark and Ron once said there's like a free algebra of like adjectives on modular forms, modular and mock modular, nearly. You know, you could say quasi nearly mock, almost modular or something like that, and they're all kind of modular in the same way. Quantum modular forms. Anyway, I like to explain that all these like whatever algebra of words and modular forms are all kind of modular in roughly the same way, but every quantum modular form is quantum in its own way, just like just a little anecdote enough reference or whatever. But anyway, so quantum modular forms is a huge topic. It's more of a it's not actually a formal definition. Like when Zaghi said what's a quantum modular form in the paper in the survey where he defined it, he left the definition intentionally vague, and it can cover many different types of things, and they're not strictly modular, right? Because strictly modular things on the set of rational numbers or on the cusps are essentially just locally, they're essentially just, they only take finitely many values, so they're almost constant functions, so they're kind of boring. So, right, like a lot of the examples of quantum modular forms, like I mentioned, the mock, you can take the limits of it from above, and then you can look at the residual stuff that lives at the cusps, and you get some quantum thing. Zaghi actually doesn't count those as real, those are kind of the cheating ones. He doesn't like them as much, he doesn't consider them as deep of examples, because they really should be something that is only defined in the rational numbers, and it may come later by some secret means that it actually is a projection of something in the upper half plane, but it should be something that a priori does not come from the upper half plane, what's really there. But anyway, it's like quantum modular forms include so many different examples, and they're not really exactly modular. So some of them do come from limits of these things, but it's really kind of a different topic, I guess. Yeah. But well, false are morally the same thing as partial theta functions. There are like identities relating the two. So if you're studying false, it's essentially equivalent to this theory of studying partial. And for like a long time, there were lots of things. There were lots of combinatorial applications. They rose in Lie algebra. They rose in physics. So people study partial theta functions. They didn't know what their modularity properties were, but Schneider and Patchen recently figured out the modular completions of those things too. But that's, well, I guess it's a couple years old, but that's kind of the cutting edge now. So yeah.
You modify them because it's quite long.
Yeah. But yeah, anything that's some kind of theta function in many of these different contexts, I mentioned the Maass, the partial, we didn't have as much time to go into those. All of these different things, they're all kind of Vign&e's theorem in disguise. They all roughly work the same. But like, yeah, but it can take like a decade or a couple decades for people to like realize the right way to apply Vign&e's theorem. So it's like deceptively simple.
How much of it generalizes to like higher dimensional abelian varieties? For example,
yeah.
What I mean is, let's say I want to do a Siegel theta series.
Yeah.
Not just the standard theta series over SL to Z.
Well, that's a good one. Yeah. So okay. Well, what do we want to generalize to abelian variety? Yeah. So do you want to make like Ziegel modular forms out of this and stuff like that?
Just I was saying that in this case of Siegel model form, P is exponential.
Yeah.
Use the back and forth, but it's one of the simple solutions.
I guess I could imagine there's a generalization to being wrong in this context, but I don't know. Do you happen to know generic? I probably is.
The paper on definite Siegel forms.
Oh, right. So they must have worked. Right, so you're right. So yeah, there's a relatively new paper of Sonder and his former postdoc about exactly is eagle indefinite data functions, and yeah, I haven't read the paper super carefully, but like I agree, I'm pretty confident that it is a variation of this. So I'm not sure like in the literature like has a complete general version of Vign&eacute been written down or not, but like I would believe it's true, and at least some variations have certainly been written. Yeah. But yeah, you should be able to do that. That's very cool.